Hello, in this video we are going to continue with the topic of magnetism and matter, and we'll be discussing the last part of it, that is the magnetic substances such as the different types of magnetic substances, where we have the dia, we have the para, and we have the ferromagnets. In case of these three types of magnets, they have different properties. The para and the ferro, they have almost similar properties, but the diamagnets, they vary. We'll be discussing about how they acquire these kind of properties, or what leads to them acquiring such properties. Now remember, what we had discussed in the previous video is that we had mentioned that a current loop behaves as a magnetic dipole, and no going by the direction of flow of current. If the current flows in the clockwise sense, then it is a south pole. If the current is in the clockwise sense, then it is a south pole, just like this is the south pole. Whereas on the other side, if you observe it, if it is it will definitely look to be in the counterclockwise sense from the other side, so it behaves as a north pole when the current is flowing in the counterclockwise sense. Now an electron, this is a highly magnified view of an electron. Now the electron does two things as it revolves around the nucleus. This is the nucleus. Obviously the sizes given here are not really uh, to the scale, but the electron revolves around the nucleus, right? So it revolves around the nucleus, and in the process it completes a circular path. And because of this circular path, the electron being a charged particle, making a circular path is nothing less than a current loop. This also forms a current loop, and this current loop uh, will have it does that in a certain time period. So it has a current, and the current that flows is can be multiplied with the area of the loop, and then we have the magnetic dipole moment that we have discussed in the previous videos. And with that, well, this is the orbital case, and you can say that the magnetic dipole moment in this case is an orbital magnetic dipole moment represented by ml, right? But to add to that, it also has its own spin. It spins about its own axis. The electron spins about its own axis. This probably is its axis. It spins about that axis, right? And that also constitutes the magnetic dipole moment, and this is the spin magnetic dipole moment. A sum of these two, that is the orbital dipole moment plus the spin dipole moment, the vector sum, gives the net magnetic dipole moment, which is associated with the given atom. Now, with all this available to us, now we can discuss about the diamagnets. Well, the diamagnets they are the types of substances which are weakly magnetized, and they are magnetized in the direction opposite to that of the magnetizing field. Now, what actually happens over here? Well, initially, in the absence of field, what happens is that external field, that is, in the absence of the external field, the magnetic dipole moments, the orbital as well as the spin, they add up to cancel out each other, only to cancel out each other. That means they are directed in opposite directions. So they add up to cancel out each other, and hence there is no magnetism. It exhibits no magnetic character in the absence of the field, external field, that is. But in the presence of the external field, in the presence of the field, what it does is they add up, they are aligned in a way, they are realigned, to say, or even reoriented along a certain line, and that line being in such a way that they do have a net magnetic dipole moment, but it is directed opposite to that of the external field, which is magnetizing it. So this is more or less the case with the diamagnetism. And what about paramagnetism? Well, it's also the same thing in case of paramagnets. The same thing being that the paramagnets do possess a zero magnetic dipole moment in the absence of the field. So this is the same. It's the same in this case, that is ML and MS. They add up to give you the value 0. That means there is no magnetism or no magnetic property shown by the paramagnets in the absence of the field. But however, in the presence of the field, you do have a value M being equal to ML plus MS, but that is directed along the magnetizing field. So that is directed along the external magnetizing field, and so it is weakly attracted. So it is weakly attracted to the magnets because it is in the same line, and this is weakly repelled. This is weakly repelled. That in case of uh, diamagnets. So what happens in ferromagnets? Well, in ferromagnets it's a bit different thing. In case of ferromagnets, the alignment is somewhat different, in the case that you have the here also, in the absence of the field. So suppose this is a plate, a ferromagnetic cross section, and what we observe over here is that they are aligned in a way. Let me draw that for you. The net magnetic dipole moment cancels out, as the alignment, even though they have a certain magnetic dipole moment here, here, here and here, you have four regions where you have four different directions of the magnetic dipole moment. These dipoles, they do have a dipole moment, but they are aligned in such a way that the net magnetic dipole moment goes to 0. Now as they are exposed, now this is in the absence of external field, magnetic field, of course, and as they are exposed to the external field, gradually what they do is the area um, of this alignment changes. So this is now having a greater area, that is all the dipoles up here in this region, they are now directed. They were directed, but this area has somewhat increased in its increased as compared to the others which have decreased. The net dipole moment here was like this. Here the area has reduced considerably, and here the area has reduced as well. So, and gradually, on applying the external field, so this is the external field, and as you can see, they are gradually aligning themselves along the external field. So after a while, what we find is that all the portions, all the segments that we had considered in this figure, in the first one, they are all aligned along the same direction, and this is strongly magnetized. So they are strongly magnetized because they do have a structure initially, right from the very beginning. As you can see, the segments, let me name them: 1, 2, 3, 4. As you can see, all these segments are having a net dipole moment, and they are very structured in their alignment, as opposed to the case of paramagnets. Even though they are weakly attracted, but these are strongly attracted, of course, and attracted. They are strongly magnetized and attracted. The paramagnets are weakly attracted. Well, that is because the alignment is not as perfect as in case of ferromagnets, which was here, which is shown in this figure, right from the initial point. They are aligned, but the structure within the paramagnets, it is not so disciplined as you can see in case of ferromagnets, and that is why it is easier to magnetize these ferromagnets, and they get magnetized very strongly. So this is the basic difference between the para, ferro, and diamagnets. And so to speak of the difference, we can, however, tabulate the differences, which will be a better way of understanding them. So we have the diamagnets, we have the paramagnets, and we have the ferromagnets. Well, to start off, these are obviously weakly repelled, while these are weakly attracted, and these are strongly attracted to the external magnet that is provided to them. And then when they are placed in the field, in the external field, they are directed opposite to the external field. They are directed along, and so are they. And then if you have come across the previous videos where I have discussed about the relation between the relative, I'm writing it over here, for the relative permeability mu r, I'm writing it here at the top. Mu r is equal to 1 plus chi. Chi is the susceptibility, or it tells us that how much a given magnetic material is susceptible to get magnetized in the first place. And susceptibility is just the ratio of the intensity of magnetization, or the capital M, that is the magnetic intensity per unit magnetizing field, and so it is just M by H. Now this is for the external field, which will be the same if we are to consider the case of having testing the magnetism of dia, para, and ferro, and we expose them to the same external H. Then The magnetization in this case, in case of a diamagnet, well, the magnetization is dipole. It is simply dipole moment per unit volume, magnetic dipole moment per unit volume. Now, the magnetic dipole moment per unit volume, as you know, the magnetic dipole moment in case of diamagnets is directed in the other sense, or in the opposite sense, and as a result of that, considering the vector, this term becomes negative as compared to the external field in case of dia. And because it is negative, this entire term becomes negative. That is, susceptibility is negative in case of the mm, diamagnetic material. So susceptibility in case of diamagnetic materials is negative. It is slightly negative. So it is slightly negative in case of diamagnetic materials. In case of paramagnetic materials, it will be slightly positive, because they are aligned along the external field, so they are slightly positive, because M here will be directed along the direction of the external field, and this is obviously has a large positive value. Highly susceptible. And because we have this relation as in case of the relative permeability of the given substance, so the relative permeability, because of this kind of a value of susceptibility, the relative permeability is obviously less than, is going to be less than 1. Mu r will be less than 1 in case of it won't be negative though, because there is a 1 over there, and because chi is slightly negative in case of dia, so obviously 1 minus of something very small decimal value, so this will be less than 1, this will be slightly greater than 1, and this obviously will be much greater than 1 in case of the relative permeability, as far as that is concerned. And it's about a very high value. That is, for soft iron it is nearly 8,000, soft iron being a ferromagnetic material, 8,000 for soft iron. Then we have the next point of difference between these materials. The diamagnetic materials, they are unaffected unaffected by any change in temperature. So they are unaffected by any change in temperature, but there's a point when if a given metal is uh, is cooled below its critical temperature in a given magnetic field, so I would add a note over there that if a given metal is cooled below, there's a certain critical temperature for a given metal, below its critical temperature in the presence of a field, in the presence of an external field, then what it will turn into? Well, it will achieve superconductivity. It will be a superconductor, and a diamagnetic substance. Well, that is the case in for diamagnetic materials, so as to say, because the materials become diamagnetic in the presence of the external magnetic field, and this is a perfectly diamagnetic substance. Perfectly diamagnetic substance, as well as it also turns into a superconductor as well. But what about the case with paramagnetic substances? Well, they are just in case of temperature, the susceptibility of these paramagnetic materials, they that is inversely proportional to the temperature. And in case of ferromagnetic substances, it's the same thing. That is, the ferromagnetism, the property of ferromagnetism decreases with the increase in temperature. It's quite evident because you have the orientation of these net dipole moments in these domains. If I forgot to tell you that these chambers that we use, that is 1 2 3 4, 1 2 3 and 4, they are known as the domains. Okay, so they are called as the domains. And in these domains, the alignment is, if they are aligned in a proper manner, with the increase in temperature, these dipoles present over here, these dipoles that are present over here, they can get excited, and with the excitation they tend to oscillate, and thereby are reoriented and lose the ferromagnetism, lose their ferromagnetic characteristics. And so this is more or less the complete difference, or the distinction between the dia, para and the ferromagnet. They're easy to remember because they are somewhat interlinked, and with the properties that I have just discussed, it will be easier for us to actually know about the concept of dipole moments cancelling out each other, and being directed in the opposite sense. In case of dia, in case of para and ferro, they are more or less in the same direction, and in case of ferromagnets, they are extreme cases because of the disciplined kind of domains that they have, as seen in the picture above. Now we have come to the last bit of this magnetism and matter case, and in that we'll be discussing about the Earth's magnetism. Well, the Earth's magnetism, as quite evident from the name of the topic, we'll be discussing about the how the magnetism of Earth affects us or works, so as to speak. Now, if I suspend a bar magnet and its north pole, it points to the north, while its south pole points to the south, geographic north and geographic south. Well, in that case, we have the Earth's external field. Um, the lines of force that will be emanated from this will be somewhat like this. You might have done experiments by putting iron fillings, or even by using a compass needle, which will help you to, get these lines of force or trace these lines of force. They will be directed towards the south pole, and directed away from the north pole, as that can be seen, and some of them will be moving like this. And remember, none of the lines of force can intersect each other, so you have these kind of lines of force. If you start tracing them, you'll have multiple lines of force starting from the north, ending at the south pole like this, and these lines of force at the top and at the bottom, there will be continuous lines. Now there will be points where these lines of force will be affected by the Earth's field, and there somewhere they will be completely cancelled by the external field of the Earth, and those points therefore won't have any magnetism uh, linked to them, and they are definitely these are the Earth's field now, which will be obviously affected by the magnet which has been suspended in space. So these are the Earth's magnetic field. They will be unaffected as they move away. So this is the Earth's field. This is the field of the magnet, and these are the neutral points showing no magnetic property whatsoever. How does the Earth get its magnetic field? Well, the Earth has a magnetic field of its own because of the motion of the electrons and the ions present in a molten state within its core. So the molten core of the Earth, the magnetic field of the Earth is due to the molten core having magnetic materials, which provide a resultant magnetic field. And that is the Earth's magnetic field. Remember, the Earth's magnetic field is a very, very important feature, and as you might have come across in various sites, or even you might have come across various videos in Instagram showing the formation of the auroras due to which is due to the cancellation of the magnetic field from the sun towards the earth. These are cancelled by the earth's magnetic field themselves, and you come across these beautiful auroras at different points on earth. uh, and in the other way around, this is a simple demonstration of how the fields cancel out each other. The other way around, of course, is that if the south pole is directed towards the north of the earth and the north pole is lying on this side, what you have is that the south pole, the lines of force will be entering over here, and of course from the north pole of the given magnet towards the south pole of the given magnet, and the lines of force will be moving like this out of the north pole. Here you have the Earth's field will be like this. But in this case, what you have is that there will be no neutral points along that horizontal axis, but they will be right along the axis of the magnet that is over here. Here you will have a neutral point. Here also you will be having a neutral point. So the neutral points in this case, let me name them as N1 and N2 because you will be confusing them with the north and the north pole, N of the north pole. So these are the neutral points in case of the this is north to north, geographic north, and this is the north to the geographic south. And this is how the magnetic fields interact. Well, that's not all. What we are going to discuss a bit further is the various terms that are associated with the Earth's magnetism, particularly known as the magnetic Earth elements or the elements of Earth's magnetism. Now, in these are some of the terms that are associated. Here we have the first term that is known as magnetic declination. Then we have magnetic inclination, which is surprisingly called as dip. I'll tell you why. It's quite interesting. At least I was amazed. And then the horizontal component, the popular one. Why is it popular? We'll be discussing that as well. Horizontal component of Earth's field, magnetic field, of course, which is H, the Earth's magnetizing field. Well, in case of the first term, that is the declination, it just tells you how much does the Earth's magnetic field or magnetic meridian declines with respect to the geographic meridian. So here you have this is more or less the shape of the Earth, and this the tilted axis, the geographic north and the geographic south. And with respect to that, you have the Earth's magnetic meridian, and it's, as you can see, is a bit tilted. It's not aligned with the geographic meridian. So the tilt is what we call as the declination. So that is known as the declination of the Earth's magnetic field with respect to the geographic meridian. What about the inclination? Well, to know that, we have to consider the three-dimensional case. Now we will be considering supposedly a surface over here. Let me give that to you in another ink. So I've considered a surface over here. Obviously, the surface that we can consider on the Earth will be completely flat, because it's a big sphere, and a small surface of a big sphere is obviously a flat surface. So we get this kind of a flat surface, and as you can see, that line, the magnetic meridian, was somewhat inclined with respect to that surface. So this is that surface, the axis along the surface, and that line lies along the surface. So this is the horizontal line passing through that center of the Earth, and this now gives me the inclination. It's the dip from the surface, as the inclination, which is obviously the same thing. Inclination with respect to the horizontal axis uh, of the horizontal axis passing through the hemisphere of the Earth, so as to say. Now, if I'm considering different points, different surfaces, so let's take the example in the upper figure over here. And if I'm using that surface that is somewhat like this, I keep it over here as somewhat like this. Now, what happens to the inclination over here? Well, it obviously changes, doesn't it? Obviously changes. Now here is the surface. Now the inclination is something different, like this. So the inclination always keeps on changing with respect to now this that we obtained is obviously uh, with respect to the geographic meridian, right? So the inclination in that case was over here and here. This is the dip, and this one is not, that's not the one over here. This is the dip, and yes, this is the dip over here. So let me redraw it for you, because the horizontal hemispherical line is not this one. The hemispherical line in this case will be parallel to this one over here. So as a result of that, you will be having an inclination like this obtuse, obtuse. I'll redraw it for you for clarity. This surface is over here, the line passing through it, this is the horizontal line probably passing through it, and we have the center of the earth over here. We'll consider a hemispherical line to be cutting the earth into halves, and from that you'll be having a certain inclination to this surface, and this inclination over here is equal to the dip that we obtain over here. So at every point, let's just look at the top figure again. At every point you'll be having different inclinations, of course, and with these inclinations available, now this was obviously on those surfaces that I'm showing on the circumference. It can be over here on this surface, getting a three-dimensional view. It can be over here on this point on that surface. Remember, this is in the form of a sphere, not a circle that we see over there. Now with these angles, different angles available to us at different points on the earth's surface, you do have two components of it, because the earth's field is H, that is the magnetizing field of the earth. It will definitely be having some component, and the horizontal component in this case is some R is the resolving, the resultant, so as to speak. We can take the resultant component, a resultant field of the earth. So this is the resultant field of the earth, and its cosine component with the angle of dip or inclination is the horizontal component of the earth's magnetic field, and its vertical component, that is sine of that delta, is, let us say, it is V. And this actually helps us in how does this horizontal component affect us. Well, the horizontal component affects various things, because this horizontal component will be aligned along the surface of the earth. In that case, aligned along the surface of the earth, the horizontal component, so various magnetic substances, or even and because this is the earth's magnetic field, so obviously it has a greater magnitude, and because of that it will affect different kind of bodies, charged particles which are in the atmosphere, because the magnetic field affects the moving charge, and a net force may act on it due to the uniform magnetic field that is present at that point. So these magnetic fields, to know the horizontal component of the earth's magnetic field, is quite essential in a given region, and that is why it is helpful. To give you an idea about the value of these fields, what we have is that at the poles this will be completely absent. Why? Because theta delta there is simply equal to 90 degrees. So at 90 degrees, delta is equal to 90 degrees at poles, and as a result of that, H is absent at the poles. And in case of the equator delta is equal to 0 degrees in the equator, and for that you have H to be having the maximum value that is equal to R, which is the case every time. And these are just simple short things that you need to observe uh, while studying this portion associated with magnetism and matter. However, the value of the declination, that is theta, that keeps on changing because the earth's magnet, the molten material, keeps on floating or rotating itself. It rotates in a different at a different speed within the earth interiors, while the exterior crust, that rotates at a different rate. So over the years there have been changes, there have been short-term and long-term changes in the value of the declination, as well as, in fact, over the formation of the earth. Over that period, it has undergone complete rotational rotations, so as to speak. So these are some of the things that we were to discuss in this video, and this ends the magnetism and matter portion. We'll be doing few numericals related to this topic, but that will be in the numerical section of the playlist. And that's all for this video. Thank you for watching.